Forces team, and we're going to give you guys our final design presentation on our vertical balance detector. I'm Alex Helander. This is Isaac Lane, Nick Kwiecinski, David Mackey, and Noah Kraus. And our primary advisor is Professor Will, and our secondary advisor is Professor Johnson. So here's the agenda for today's presentation. We're going to give you the background and the solution, and then we'll go into our final design. We'll break down into the different aspects of it with the physical device, the transmission, and the programming side of everything. We'll go over our test results, and then we'll go into the future improvements, what we learned, conclude this presentation, and you'll have one last opportunity to ask our group any questions that is on your mind. So the background for our project. Professor Will has a friend named Joe Schlavine, and he approached him after he was diagnosed with Parkinson's. Parkinson's disease is a neurodegenerative disorder that causes imbalance, tremors, and rigidity. So one of Joe's main problems is when he stands still, he has a tendency to start to lean forward, and he will fall eventually. And he can't feel this happening to him. So he would want us to design a device that would alert him of this starting to lean or him losing his balance, and so that he can perform corrective measures and prevent any falls in the future. So I'm going to hand this off. So this is our solution. What we came up to the device is we will go more in depth with it further in the presentation. So basically on the chest we have an accelerometer and that calculates the linear and angular acceleration. That sees when he's starting to rock forward with pressure, and then we have pressure sensors on the feet as well to see if his weight's starting to shift forward or backward. We'll go into the protocol, the states later, and now I'll hand it to Isaac to go over the components of the device.
Beautiful. So yeah, I'm going to talk about the physical aspects of the device and just the notification system. So for our device, we have a main node, which is around the chest, then two secondary nodes that are around the ankle. And for the casing for that, we modeled it in SolidWorks and 3D printed it. So, so for the casing, we have these clamps on here that clamp together from top to bottom. You know, the secure fit. We have these posts inside here that add to that keep the internal pieces together. And then we have this little hole here so you can charge the casings for the nodes. And then for the notification system, so for the visual aspect, we have 4 lights that represent the 4 different states that it'll be in. So the colors are blue, green, yellow, and red. Blue indicates if the user's walking. Green indicates if they're in like a neutral state, so if they're just standing. Yellow indicates if they're leaning, so if they're leaning forward or back. And then red indicates if they're in imbalance, so if they're about to fall. So then if it's in the red, there also be a piezoelectric buzzer that goes off so they're able to hear that they're about to fall. So for the main node, the physical parts of it is the 3D casing, the LED to let them know if they're about to fall. It's powered with a lithium ion polymer battery. Also has an Adafruit precision IMU, so it measures the angular acceleration and the angular velocity. Also has an Adafruit M4 Express microcontroller in it, our radio transceiver, and an athletic wrap to hold it around the chest area. And then for the secondary node, it also has the 3D print case, LED, the Adafruit Feather M0 microcontroller, a radio transceiver, and then it has 2 insoles. So the insoles are pretty thin and pretty flat, so the pressure sensors can read pretty well on them. We have 4 pressure sensors altogether, 2 for each foot, and those individually can read up to like 100 pounds. And then we have athletic wrap to hold the nodes around the ankle.
Thank you, Isaac. So I'm going to be talking a little bit about the programming aspect of kind of how we got everything to work, so behind the scenes. So the first step to this was how do we get all the data from where we need to go. So this involved our radio transmission. And our initial design involved a lot of each node sending out radio signals at a certain frequency, and then I was trying to work with the main node to try to get everything to sync up. So what I did is I actually redesigned the whole system kind of around acknowledgement packets. So what this means is in radio, sometimes when you're sending out a transmission and you get receive a message back that message was received. And there was the ability with these certain chips that you could put an acknowledgement packet. So that would mean sending a little bit of data, not just an acknowledgement bit. So I realized that in each of the footnodes, our data was small enough that I could put it in that acknowledgement packet. So what that means is that we have a new system design where the primary node is actually pinging node A and B for their data, rather than node A and B trying to send out a message, every 150 hertz that it has data. So this solution solved a lot of our problems that we were having with timing, because this means now we only have to we can get the data as fast as the primary node can send out messages and be pinging node A and B. So this means that the primary node is also only set up as a transmitter. So the primary node is never receiving any radio messages. So I didn't have to switch configurations, even though the chip had the ability to do that. It cut down on the time. So the next thing I wanted to talk about was the reduction of what we have here is a 5-state system on the left and to a 3-state system on the right. And so we went from the 5 states being walking, shifting, settling, standing, and imbalance, to only walking, standing, and imbalance, with the forward lean and the backward lean being intermediate states. And so why we did this is we realized that we need to simplify our system design a little bit to kind of narrow down exactly what we were looking for. So I'm going to be going through each of these 3 states and how we're detecting those. So first, I'm going to be talking about the walking detection. So I have something called the Kwiecinski number, which actually Rachel coined the term, because I didn't know what to call it. And so what this involved is, we have talked about in the past how we're using a fast Fourier transform to detect the frequencies in the walking between the pressure difference in the feet. However, when you're translating a lot of what we were doing in MATLAB to stuff that was actually happening on the chip, we realized that stuff was a little different. Like you said, in theory isn't necessarily in practice. And so with MATLAB, everything was one-to-one. We had all our data and we could get a straight FFT. However, with what we were doing on the chip, we were only using about 128 samples. And if you're familiar with how an FFT works, that means half of those was the bins that we were getting. So we only had half of 128 bins of different frequencies. So this was causing lots of issues with like resolution and low frequency noise and things like that. So what I did to solve this issue is I took the average amplitude of a range of bins, approximately 10 to 22 hertz. Now that is double the frequency, so 10 might seem a little fast, but what we're doing is we're adding both feet together, so we're doubling all our frequencies, so that's 10 to 22 hertz. And then taking that average amplitude and I'm graphing it. And then I also added a bias on the rate of change for this variable, so that means every time it detects a new one, it's only adding a portion of the last value in terms of the rate of change. So this means that it dealt with a lot of it jumping up and down. It would tend to slope up. And then I added a threshold to detect the walking. So as Noah was walking, this number would slowly drift up above this threshold, and even if he maybe stopped for a hot sec and kept going, it would still stay above that. It would only jump down if he was standing for a period of time. So this fixed a lot of the issues that we were having and actually ended up being a very efficient system. So then I want to talk about the remaining states. So standing we defined as anything that was not walking, leaning, and balanced. So this was a fairly simple state to detect, basically a knot. And so to kind of help with some issues between a slow walk and a stand, we added a standing delay. So this is approximately how long would they need until they were standing. And then forward and lean, like I mentioned, we combined the pressure differences in the node, and those were a simple threshold forward or backwards. And then for imbalance, it was a simple threshold on the angular velocity of the IMU on the primary chest node. So if you were in either a forward lean or a backward lean, if that angular velocity threshold was triggered, then we would do a state of imbalance. And what we also implemented is that if an imbalance was triggered, the buzzer did not turn off until you were back into a standing or a walking state. So that means that if you lean backwards and then you go in balance and then you go back to a backward lean, the buzzer will still sound. It's not until you regain your balance or started walking that it turns off. So what this means is that we have a set of characteristics depending on whoever is using this device. So as you can see here, I've listed all the characteristics for Noah, And these are kind of the tunes. So this means that depending on whoever will be using this device, we'll tune it to them, and this kind of adds a little bit of variability. We can put this on someone else. I can tune it up until it feels good. So up next is David, who's going to be talking about our SDRD requirements and our testing.
So going into our test results, we had a lot of success in testing. The hydrogen flow cell team performed all the testing, so thank you to them. But starting off, one of our issues that we had with our testing was that our pressure sensors weren't as accurate as we required them to be. As we did the test, we made calibration curves for each sensor, picked the best sensors. However, we found that our calibration was more than our requirement stated. So we currently stated that it should be at least an error lower than 6.6 pounds, and we found that we had an error of around 7 to 10 pounds for our pressure sensors. However, we realized that this wasn't critical to the system's performance, as we're using them as more of a relative measure, comparing them in the force differential. So we're not super concerned about this error. If we had some time to do, which we'll talk about the future improvements and how we can fix that. Some of the other tests that were performed was the actual imbalance and alert detection. The hydrogen flow cell team started a timer between the time that the device went off, alerting of an imbalance. So that means the device detected and alerted the user of an imbalance occurring, and the time between that and when NOAA had to take a recovery step. So this would be when the user would have to take their balance. So usually they'd step forward and catch themselves. We found that this time was about 1.03 seconds, which is about double the requirement of 500 milliseconds. Now, we're still unsure if this will be consistent when we apply this to Joe, but we're very happy that this was able to succeed with this for NOAA. We also had several endurance and durability tests. Specifically the battery life, we had NOAA wear this device for more than 6 hours, and that was successful. Our theoretical lifetime for one charge was about 25 hours. So we were happy that the device could last for that long. Also, we had NOAA do 20 jumping jacks while the device was strapped onto him. This was to test the harness, aperture, and the wrapping. Basically, we wanted to make sure that there was no shifting during daily activity. After he did the 20 jumping jacks, we could see negligible movement, and so we were very happy and okay with that system. Finally, each node of the device was dropped from 1.5 meters per our SDRD. Our nodes were durable enough that we had no fractures or cracks. Also, none of the internal components were shifting around due to the posts inside the casing, so we were happy with those tests. Finally, I wanted to give you guys an update on our budget. So our original budget had a price of $600 for our device. We ended up spending about $265, which was very helpful. This is a figure broken down into the separate subcategories. As you can see, they're mainly about 20 to 40% of the actual price. This is due to some contingency and miscellaneous budgeting concerns. However, you can notice that the mounting is significantly lower than we anticipated. This was due to the fact that we did not follow up on any harnessing, as we felt like the athletic wrap was durable enough and sustainable enough. Also, we found that our insoles that we're using for our pressure insoles was a lot cheaper than we expected. We anticipated trying to use some Dr. Scholl's high cushion insoles, but we realized that the flatter material was actually better. Flatter, thinner material was better for our design. Now I'll pass it off to Noah for some takeaways.
Thanks, David. So if we had more time on this device, we had a lot of ideas for what could be improved. For one thing, the aesthetics. I think our device looks great. It's compact. It can be hidden under clothes. But if it was to be sold on market, then we want it to look a lot more sleek, something that people find attractive, something that looks like a finished product. Additionally, we could have invested in an actual harness rather than just the athletic wrap. The athletic wrap is applicable and works great, but the harness would be easier just for one person to put it on. Additionally, a custom PCB, that would have helped us clean up a little bit of the wires inside our device, provide a little more organization, and just make it look like a finished product. Additionally, we could have invested in more sensors or better sensors. So the sensors we have now, they're sufficient for our project for detecting imbalance, but by including more sensors or by having better sensors like these these foot sensors here, we could have better tracked his movement, or my movement, I guess, and we could have limited the amount of false positives that we're actually getting, because we would know exactly where I'm at all times. We could have performed a lot more tests and put those through a neural network. This would have given us a better idea of exactly what walking looks like for a lot of different people, and take some of the work away from our end and given us a more accurate idea of what the thresholds should be for walking and for leaning for falling. Finally, we could have included an automated calibration. Right now, to calibrate it, it requires one of us going into the code, looking at all the thresholds, and then adjusting it like step by step for the specific person. By having an automated calibration, ideally this would have meant that like the device would tell the user to do some kind of test, like a leaning test or walk for 5 seconds, and then it would automatically find that threshold for those tests. This project tested a lot of our skills as engineers. One of the main things was researching design concepts. That's what we did most of the first semester, was just looking at how can this metric of balance be tested, and how have other groups done that in the past. There weren't a lot of answers, honestly, and this is kind of a new thing for us to just kind of be creative with and finding it for ourselves. Additionally, we did a lot of modeling with CAD, at least the mechanicals did. This was how we did all of our casing, and Additionally, we did part selection. We had to do a lot of research to make sure that the parts we selected were correct for our application, that they were cheap, but they were also worth the price that we were paying for them. We did RF communication with this device, and this required some research into timing and making sure that the code we have won't be affected by having it be wireless. Finally, we did a lot of coding on the microcontroller. That was mainly what we did all second semester, was trying to get our Imbalance algorithm to work on the microcontroller. Finally, we did some prediction mathematics. So in order to predict when he was going to be in balance, we needed to look at different ways we do that with mathematics, and we ended up using the fast Fourier transform for detecting the walking. So we learned a lot of lessons about the design process. One thing was that we found we should prototype and build like right away, because this would allow us to find those problems that are going to occur when you do start building, and start counteracting those problems right away. Defining our parameters for what our device will do, we have to be really careful of how we word it, because as a medical device, there are liabilities to be held if it doesn't accomplish exactly what it says it's going to do. So we have to be careful with how we word that. Finally, we had limited access to our customer. As Joe lives in Georgia, we couldn't really work with him to make sure it was going to work for him. So we had to work around that by finding a test subject that matched his metrics a little bit, his height and his weight. And we also had to just communicate with him along the way through email and through video about what kind of changes he would like to see in the device. We learned a lot of lessons about teamwork. So we learned how it's important to communicate. It's important to communicate early. It's important to communicate often. You want to document any changes you make on the project so that your teammates can see that and they can track what changes need to be done still in the future. And this requires a lot of organization. So in conclusion, we described to you guys how balance detection is a need for many people, such as those with Parkinson's. We described to you guys how our device accomplishes this through planar pressure tracking and through the motion of the torso. Finally, the device successfully passed most of its tests, and we learned a lot along the way. Thank you guys for your attention. Are there any questions? Yes,
I got 2 questions. Can you do it slide 11?
That's all.
Yeah, so Noah was saying that when you're calculating the bins for the FFT, you were just doubling the data coming from the feet. So couldn't you just have one sensor in one foot and then just use that as a number if you're doubling the foot?
So, let me clarify your question a little bit. So you're saying
the having 2 sensors, 1 in each foot, if you're doubling it, it kind of doesn't really do anything besides act as a dependency for.
Oh, okay. So you're asking why are we doubling it?
Why don't you just have 1 sensor?
Okay, why
that
don't
double
we have one
sensor?
sensor? I think I may have misexplained the doubling thing. We're not doubling it. We're adding them together. So we have
adding them
2.
together. Yeah.
So is it?
Well, if you have 1 foot that you end up adding them together, wouldn't it be good enough to just have 1 foot? Basically, I'm saying is like, do you really need 2 feet to.
Okay. Okay. So he's asking why do we use 2 separate data streams on each foot,
Yeah.
not just one? That's a very good question. Why we did that is because if you think about it, you're taking a step. Your heel goes down, but your heel goes up on the other foot. So basically, because we originally only had 1 foot in the system for a long time, and when we added the second foot, because for most people, when you step, it's the inverse of what the other foot is doing. It doubled the time on everything that we could detect. Because let's say if you only had a sensor on your right foot, but you took a step with your left foot, you wouldn't be able to detect that you took a step because your right foot would still be on the ground. Does that make sense?
Yeah.
That's why we use 2 feet for
Okay.
engagements. Yeah.
On your data flow diagram, it said you were still sending data to a computer. Are you doing that after everything's done, or are you doing that in real time?
So he's asking if we're sending data to the PC receiver. You want to go to that slide? Just one, two, focus. It's the video. So if we're sending that after everything is happening. So what I have that sending out is basically every time it detects a different state, it currently sends out a message to the PC receiver, but it doesn't wait for a response. So it sends it out, has no idea if it's getting picked up or not. That's kind of the idea of like, this thing should be able to run without confirmation from another device that it's being received. So that's what the PC receiver is functioning as.
Can you go one slide back forward? Yeah, so with this decision thing, one question I have is, how does he know? So if he has from what I'm understanding is he doesn't have any sense of when he's standing still, when he's off balance, he doesn't have that sense anymore. So if he gets this yellow light or this red light that's saying you're imbalanced, how does he know whether to step forward or step backward in that case? Because if both forward and backward have a yellow LED, and I'm leaning forward and don't have a sense of that, then if I just pick randomly, I have a 50-50 chance of just collapsing.
So what Alec asks is, does the user know like which direction he's falling if he can't? Even if he's alert if he's falling, how does he know how to correct himself because he doesn't know which way? Is that correct?
Yeah.
Alright. So Joe, first of all, he primarily falls leaning forward, so that's what he probably will anticipate that more often than falling backwards, and it's a lot harder to fall backwards. However, what he does when he falls, either way, is that he crunches like kind of down a little bit to like lower his center of gravity to prevent himself from wobbling. So any alert for any which direction, that doesn't really matter for the way how he corrects himself. But in the future, we could look into that and maybe change the tone or change the pitch depending on the direction he's falling.
I think I also want to add on that real quick. It's also valid that like the idea with the LED facing outwards is it's more of an indicator for the people around him, but the audio alert is specifically for him. So like you said, we could vary the whatever. But the issue that we're having is like there's an LED down here. It's not like he's going to be walking around like this, looking at the LED the whole time. It's just the way that the system is designed.
What was the desire to go with an audible alert instead of a tactile, let's say a vibration on the chest? I would figure if you're in public, it'd be probably less embarrassing if you just had something to vibrate on your chest and you're hearing a beeping noise.
So Professor Blood asked why we chose to go with an audible alert instead of a tactile. Yes, we figured that might be slightly more embarrassing if it is audible. However, if someone's around them and if it's like audible, they can see the light as well, but if they like don't notice the light or anything and they hear it and are aware of his condition, they can be able to help him too. Whereas if it's just him that's able to feel the alert, he won't be able, like other people may not be able to help him because they cannot feel that alert.
So his main desire was to have other people help him out.
Not primarily, but it was just kind of a thought that we had. It's morally for him, but that's also another benefit if he gets past the point where he can't correct himself, and if he's talking to someone, they can help him as well.
So I'm just wondering, like, did he express that he wanted other people to help him out, or was that something that you guys just came up with?
So you basically asked if he expressed himself if he wanted other people to help him. No, he did not, but we just figured that we did choose that ourselves because we figured it would be better for other people to be aware if there's a potential of them to fall.
And that was one of the discussions we had with them in our customer review meetings, is whether he wanted the tactile thing or a sound. And I think he had told us that he didn't really hear either way, and so we thought the sound might have more benefits than the tactile.
Jackie.
With the athletic wrap, can someone put this on by themselves?
I can, yeah.
Yeah.
But it is kind of difficult because I have to kind of put one little wrap on underneath my arm and then grab it from behind and bring it back around. But,
Okay, I was just curious because if he has Parkinson's, he probably doesn't have the same fine motor skills.
yeah, exactly. So yeah, I think he might need help applying it, but yeah.
Well, so Jackie asked if he would need help or anything for applying the athletic wrap. Well, with our customer, he doesn't experience tremors as much. His issue is primarily just Imbalance, and he's doing really well right now. He says a lot of his symptoms are actually starting to decrease, which is great. But like with tremors or anything, he doesn't experience that as much. So for our customer right now, athletic wrap should be fine, and that's also kind of one of the reasons why, if we were going to improve this project, that we would make a harness to make it easier in the future.
Alright, so what time we have? Thank you.
Thank you.